students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as atoms, molecules and nuclei. Now, let's understand what is optical pumping. Right? Now, let's assume that you have atom in the ground state. These are two atoms that I have in the ground state. Right? Let's assume this is my energy level is E1, this is my ground state. Right? Now, when you have light falling on this due to photon energy, some energy will be acquired by these electrons, some energy will be acquired by these atoms, as a result of which the electrons in these atoms would go into excited state, right? So in that case you would have them going in excited state, right? Let's assume that they go in state E bar 2 is the energy level where they go, right? Now at this energy level, this is my excited state. The life of the electron at this high energy level, since it has acquired energy, that means it is going to be in unstable state, right? The life of this, the electron or the life of the atom in this state is going to be approximately 10 raised to minus 7 seconds. The life of the atom in this state is going to be approximately 10 raised to minus 7 seconds. Now that time interval is too short for a photon to hit it, so that I can have amplification of the light beam. Now what it does is it falls down to another energy level after 10 to the power of minus 7 seconds. It comes to another energy level. So the electron comes here. Let's call this as energy level E2. This is metastable state. Right? Now the advantage of this metastable state, it is at an energy level lower than the excited state, but the life of the electron in this state is going to be approximately 10 raised to minus 3 seconds. Right? Now that time interval is sufficient for a photon. That time interval is sufficient for a photon to strike this atom before it comes back into the stable state. So from here the atom is going to come back to its stable state. The atom which has the electron in excited state is going to come back into its stable state. While doing so, it is going to give out a photon energy. It is going to give out energy in the form of photon. It is going to give out energy in the form of photon, right? And if this photon, this atom is, if I strike this atom with an external photon, then whatever is the frequency and the wavelength of external photon, this photon shall also have that frequency. That's how I will control the frequency. And this whole process is called as optical pumping, wherein I take the atom from ground state first to the excited state, from excited state to the metastable state, and from the metastable state back to the ground state. Fine, do we get this thing here? Okay, let's write this down. So we will say this is how you would have laser produced. This principle is called as optical pumping. Okay, so let us consider a system in which most of the atoms are in ground state. Most of atoms are in ground state. Right? Now let E bar 2 and E2 be the excited states. right? Let them be the excited states of the atom where E bar 2 is still higher than excited states of the atom where E bar 2 is greater than E2. Fine. Now, let us assume that if this system is bombarded with photons having energy, this system is bombarded with photons having energies, with photons having energy E bar 2 minus E2, the atom in the ground state will absorb those and the photons will get raised to the excited state. So if I bombard the atom which is in ground state with energy, obviously it will go into the excited state, it will absorb energy and go into the excited state. The atom in the ground state will absorb the photon and get raised to excited state. E bar 2, right? Now, but this state is highly unstable. Right? This particular state is highly unstable. That is, it has a mean lifetime of 10 to the power of minus 7 seconds. Therefore, the state quickly decays. The state quickly decays to the state E2. By emitting heat radiation. Obviously, if it is coming down, it is going to give out some heat energy. Heat radiation. By emitting some heat radiation, the mean life of the atom in state E2 is 10 to the power of minus 3 seconds, which is quite large as compared to the mean life of the atom in state E bar 2, which was 10 to the power of minus 7 seconds. I can say the mean life of the atom in state E2 is of the order (10 to the power of minus 3 seconds). Right? Now, such a state is called as metastable state. Such a state is called metastable state. Such a state is called as metastable state. As the metastable state increases quickly, as a result, the number of atoms in the metastable state increase quickly. They have been optically pumped, they have gone up, they are now in metastable state. So you have large number of atoms in metastable state, which is equivalent to my population inversion. Instead of having large number of atoms in ground state, now I have large number of atoms in metastable state, which is population inversion. So what happens here is population inversion takes place, right? So as a result, the number of atoms in metastable state increase quickly. quickly, right? Now, it is found that these atoms spend more time in metastable state and finally jump to the ground state. It is found that these atoms spend more time as in metastable state they are there for 10 to the power of minus 3 seconds, whereas in the excited state they were only for 10 to the power of minus 7 seconds. So obviously they are spending more time. So it is found that these atoms spend more time in metastable state and finally jump to the ground state. Jump to ground state. Right? Now, the rate at which these atoms are excited from E1 to E bar 2 is greater than the rate at which they are going to jump from E2 to E1. Right? We make sure that the rate at which atoms are excited, from E1, that's the ground state, to E bar 2 excited state is greater than the rate at which rate of jump from E2 to E1. So if there are more number of atoms going up and less number of atoms coming down, that means the number of atoms in state E2 will automatically increase. There will be large number of atoms in state E2, and which will cause my population inversion to take place, right? Therefore, the population of the atoms in state E2 becomes greater than that in the ground state. Remember, we had this problem, Bohl's ratio, which said that the number of atoms in the ground state are more and therefore it is not possible to amplify light. Here what we have done is we have increased the number of atoms in the excited state. Now you have more number of atoms in the excited state than you have in ground state, right? I can say that therefore the population of atoms in state E2 becomes greater than that in the ground state. Right? This process is called as optical pumping, or it is also called as population inversion. Right? So what is optical pumping? It is a process wherein you increase the number of atoms in, you make sure that the number of atoms in the excited state are more than the number of atoms in the ground state. Right? So I can say this process is known as optical pumping or population inversion. Right? Once I have population inversion taking place, now a photon of frequency V, which is equal to E2 minus E1 upon H. This is going to be the frequency of the photon, enters the system from some external source, from some external source, enters the system from some external source, and collides with the atom in the metastable state, and collides with the atoms in metastable state. It collides with the atom in the metastable state, right? And stimulates the atom to jump to the ground state. And stimulates the atom to jump to ground state. It stimulates the atoms to jump to the ground state, right? So where they would have stayed there for 10 to the power minus 3 seconds, now because of this stimulation they will stay there for less than 10 to the power minus 3 seconds. This atom jumping to the ground state emits a photon of the same frequency, that is, it emits a photon of the frequency which is equivalent to the photon of the frequency that had collided with it. So this atom jumping to the ground state, this atom jumping to ground state emits a photon of the same frequency, emits a photon of the same frequency that is E2 minus E1 upon H as the incident photon, same frequency as that of the incident photon, same frequency as that of the incident photon, right? This emitted photon is in phase with the incident photon. This emitted photon is in phase with the incident photon. Right? Now there are two photons of the same frequency in the system, and they stimulate two more atoms, right? So you will have thus, now there are two photons, of the same frequency, and they stimulate two more photons, same frequency, in the system, and they stimulate two more photons, right? They stimulate two more photons of the same frequency and same phase, making the total number of photons in the system equal to 4. Making the total number of photons in the system equal to 4. Right? Now, which will again, these 4 photons will now stimulate 4 more photons, which will again have the same frequency as the previous 4 photons. Right? In this way, the number of photons of same frequency and same phase will increase twice every time. So I can say that in this way, the number of photons of the same frequency, number of photons of same frequency and same phase, same frequency and same phase increase twice every time. Right? Thus, this multiplication of photon, that is chain reaction, results in the amplification of the electromagnetic wave by stimulated emission of radiations, and the resultant light is very intense, is extremely coherent, and can be easily focused, and therefore it is called as laser. Fine, do you get this in clear? That's how you produce laser. I can say that increase by same phase, increase by twice every time. This multiplication of photon results in the amplification of electromagnetic wave by stimulated emission of radiation. Right? The resultant light is very intense. The resultant light is very intense and coherent and can be easily focused. Right? And this is called as laser. Right? That's how you produce laser. Fine, do we get this in clear? So, do you understand the production of laser? Next, let's see what are the properties of laser. What are the properties of laser? Now, properties of laser, the first property is monochromatic. Monochromaticity. Monochromaticity. Now, the laser beam is highly monochromatic. That means it contains only one frequency, right? The other frequencies are extremely weak and in intensity and hence negligible. Therefore, the sharpness of the laser beam can be expressed in terms of delta V upon V, where delta V represents the spread of frequency present in the laser beam. Okay, so I can say that it is highly monochromatic. It is highly monochromatic. Highly monochromatic, that is, it contains only one frequency, right? I can say that the sharpness of the laser beam can be expressed. The sharpness of the laser beam can be expressed in terms of the ratio delta V upon V, where delta V represents the spread of frequency in laser beam, where delta V represents the spread of frequency where delta V represents the spread of frequency present in the laser beam. Present in the laser beam. Fine, do we get this in here? Huh? V is the total frequency that is present. Now it can be noted that this is in the ratio of 1:10 to the power of 15. So out of every 10 to the power of 15 beams, only one beam has a different frequency. So the ratio of monochromaticity in the laser beam is extremely high. Fine. Next. Next, they are highly coherent. I can say laser is highly coherent. Highly coherent because the frequency and the phase of the stimulated photons is exactly same as that of the incident photon. Therefore, the beam is highly coherent over a large distance of approximately thousands of kilometers. Fine, do we get this in here? So I can say that because the frequency and the phase because the frequency and the phase of the stimulated photons because the frequency and the phase of the stimulated photons is exactly same as that of incident photons therefore the beam is coherent over very large distances. Therefore the beam is coherent over very large distances. Right? So the laser beam is highly coherent. Next, directionality. Now, the laser beam remains parallel over very long distances. It has extremely low angular divergence. It is found that a beam of diameter 1 millimeter has a divergence of about 1/60th part of 1 degree. So I mean to say that divergence is very less. 1 degree in itself is very small. If I divide 1 degree into 60 parts, that's the amount of angular divergence that it has, right? So I can therefore say a laser beam, suppose hypothetically speaking, if I were to direct a laser beam towards the moon, it can produce a spot of the diameter of few meters on the moon surface. That means it can travel straight up to that large distances. And do you get this thing here? So directionality, I can say laser beam remains parallel. Laser beam remains parallel over long distances. It has very low angular divergence. Very low angular divergence. It has very low angular divergence. It is found that for a beam of diameter, it is found that for a beam of diameter 1 mm, the divergence angle is about 1/60th part of the degree. Right, that is your directionality. And lastly, laser beams can remain focused very sharply. Again, I can say that they are parallel to a very high degree. Therefore, the intensity produced by the focus beam at the spot is very high, which is actually 10 to the power of 17 times the intensity of the incident laser beam. Right? All the beams are focused. Right? The beam is highly focused. Therefore, the intensity increases to the order of 10 to the power of 17 times. Right? So, I can therefore say that can be focused very sharply and be focused very sharply. A laser beam can be focused very sharply because it remains parallel to a very high degree. Because it remains parallel to a very high degree. Therefore, it can be focused very sharply. Fine, do we get this thing here? Next, what are the applications of laser beam? What are the applications of laser? 1/60th. Right? Yeah. If I divide 1 degree into 60 parts, that's the amount of angular divergence that they will have. Now, where do I use laser beams? Laser beams are used in modern communication system to send signal over long distances through optical fibers. Send signals over long distances. Send signals over long distances through optical fibers. Right? That's the first application. As the beam of light is highly coherent, it can travel very large distances without losing intensity. Hence, it is used to measure distances of distant objects such as moon. Used to measure distances of distant objects. Right? Due to high intensity or a very small cross section, the laser beam is used to bore a hole of very small diameter into metal plates of several centimeters thick. Right? You must have seen this. You have this video on YouTube where they've shown you an industrial process. You have a metal plate, and the laser beam is drilling a bore into it. Right? So it is used to drill. It is used to bore a hole. It is used to bore a hole of very small diameter. Of very small diameter. It is used to bore a hole of very small diameter in metal plates. In metal plates of several centimeters thickness. Centimeter thickness. Fine, do we get this thing here? Next, laser beams are used by surveyors, engineers to ensure that roads, railway lines, oil tankers, pipes, buildings are constructed accurately. So it is very useful in case of boring tunnels over long distances from both the ends. Right? Now, moreover, as laser beam is capable of producing high power and intense amount of heat, it raises the temperature in a narrow region by about 1,000,000 degrees, right? This temperature is useful for fusion nuclear reaction. So in fusion nuclear reaction, you use laser. It is used in fusion nuclear reaction. Why? Because of the extreme high intensity, it can produce heat up to millions of degrees centigrade, right? Now, it is also used in lab to study the molecular structure and the nature of chemical reaction. Used to study molecular structure and nature of chemical reaction. Right? In military, it is used to set fire to targets such as tanks, aeroplanes. In industry, it is used to drill holes. I've already told you that. Then it is also used to read barcodes, to manufacture compact discs, for cutting garments, and for welding auto parts. So these are few of the applications. It is also used in surgery to perform bloodless surgery. Then that's it. So these are some of the applications of laser. Next, let's move on to the next topic. We did applications of laser. Next, let's move on to maser. Right? What is maser? Maser is microwave amplification by stimulated emission radiation. Maser is microwave amplification by stimulated emission of radiations. Right? Now, what is maser? Maser is a device that produces and amplifies electromagnetic radiations mainly in the microwave region. Right? In the microwave region of the spectrum, whereas laser produces and amplifies electromagnetic radiation in the ultraviolet and the visible region. So the difference between laser and maser is only the frequency. In the case of laser, the frequency would be either in the visible spectrum or in the UV spectrum. Whereas in the case of maser, the frequency is going to be in the microwave region. Right? It has the same atomic process. Same atomic process means you will need to have induced absorption, you need population inversion, and then you need stimulated emission. So you would have atoms which are in the ground state, they would go into the excited state, they will come into the metastable state, have population inversion, will be bombarded with a photon. But this particular photon that you are going to bombard it with is going to be of a frequency in the microwave region. Hence, the photons that will be emitted, the amplified photons that will be emitted, all of them will be in the microwave region. Fine, do you get this thing clear? Thus, maser is similar to laser, but the only difference is that it is working at lower frequency and higher wavelength. The only difference between laser and maser is, in the case of maser, the frequency is going to be low and the wavelength is going to be high. Fine, do we get this thing clear? Now, let's write this down. Maser. Laser is a device which produces and amplifies produces and amplifies electromagnetic radiations in the microwave region. In the microwave region of the electromagnetic spectrum. Of the electromagnetic spectrum. Fine, do we get this in here? It has the same atomic process. It has the same atomic process. It has the same atomic process, that is induced absorption. Induced absorption. Induced absorption when you have population inversion. Induced absorption, population inversion, and stimulated emission. Stimulated emission. Right? So it has the same atomic process involved, stimulated emission are involved in the production of laser. Are involved in the production of laser as well as laser. So that means you are going to produce laser in the same way as you had produced laser, right? Thus I can say that maser is similar to laser. Thus maser is similar to laser, except laser is similar to laser but working with photons. But working with photons of low frequency, and higher wavelength. Right? So the principle of working of both maser and laser are same, with the only difference is that the laser works in the UV and the visible spectrum, whereas the maser covers only the microwave region, right? So you would still have spontaneous emission would be proportional to the cube of the transition frequency. Here I can say that the spontaneous emission would be proportional to the cube of transition frequency. Right? That means spontaneous emission is extremely small in the microwave part of the spectrum and therefore can be neglected as compared to the other important processes such as stimulated emission and absorption. Therefore, population inversion can be easily achieved in maser with just a small amount of optical pumping, because that whole region where the whole microwave region where I need extra number of atoms, so that extra number of excited atoms so that they can give out a photon is extremely small, right? So I can say that the spontaneous emission would be proportional to the cube of transition frequency. Now the transition frequency in itself is very small. I'm only restricting myself to the microwave region. Hence I can say that spontaneous emission is extremely small and spontaneous emission is extremely small in the microwave part of the spectrum. Extremely small in the microwave part of the spectrum. Right? And can be neglected. So there will be hardly any spontaneous emission and can be neglected. Can be neglected as compared to other important processes. Can be neglected as compared to other important processes. Processes such as stimulated emission, stimulated emission and absorption. Right? Therefore, population inversion can be easily achieved because there is going to be no spontaneous emission. I can say therefore population inversion can be easily achieved by in measure with very modest pumping powers. Fine, do we get this thing here? So do we understand what is measure? Now, so it is going to be, the whole process is going to be same as laser except that the frequency is going to be low, right? Where do I use measure? Where do I use measure? It is used in satellite communication system at the first stage amplifier. Satellite communication system at first stage amplifier. Right, that's the first place where you use it. Then it is used to determine the frequency of specific molecular transition. Frequency to determine frequency of specific molecular transition. Right? Then it can be transmitted over fairly large distances with relatively low power loss. This is why maser radio waves are found much closer to an ideal single frequency source. Therefore, they are used in radio transmitters. But they cannot be transmitted over very long distances. But over small distances, they can be transmitted with fair degree of accuracy. Okay. Masers are used as weapons to spoil the control system of aeroplanes and make them crash with additional features that the crash cannot be detached. Right? If you've seen this movie Die Hard 2, in Die Hard 2 they had shifted the whole angle at which the plane would come into the landing and would land. As a result, the plane would end up crashing. That's what the terrorists were supposed to do. How is that done? That's done by just changing the maser frequency. So if I emit maser frequency in the direction of the plane, then the radar system, the communication system of the plane would be totally disturbed and it would not be able to find out with accuracy where it has to land. Right? So it can be used as a weapon. to spoil the control system. To spoil the control system of aeroplanes. And make them crash. Then maser can also be used as a weapon system, which can be used to bombard humans, and which produces dysfunctionality of the brain. If maser is bombarded onto your brain could be totally damaged. Right? Brain automatically stops working once maser is bombarded onto your brain. Right? So it is used. Maser weapon system is so dangerous. Maser weapon system is so dangerous. That it can be used to bombard the humans. To produce dysfunctionality of the brain. Right? And most of the weapons that you see in your sci-fi movie, they are all masers, right? So maser is often observed as weapons in science fiction movies. It is often observed as weapons in science fiction movies. Right? Okay. We'll stop this here for the day. Thank you very much.